The universe as we perceive it might be far from being the whole picture. The astonishing warning from British physicist and Nobel laureate Roger Penrose is leading us into a new cosmic perspective full of uncertainties and challenges. This is not some illusory poetic imagination, but rather based on a series of anomalous phenomena captured deep in the universe by the cutting-edge James Webb Space Telescope. These discoveries are quietly shaking the very foundation of our beliefs about the origin and evolution of the universe. For a long time, the question of whether the universe is unique or just a part of an infinite multiverse has lingered in the realm of philosophical speculation. However, with the emergence of more and more data, the answer seems to be getting more complex and disconcerting. Since its operation began, the James Webb Space Telescope has continuously sent back data revealing numerous abnormal signals from the early universe. These not only challenge the existing cosmological models, but also prompt astronomers to re-examine the definition and timeline of the cosmic dawn. Those galaxies from more than 13 billion years ago have structures and masses far exceeding our expectations, as if telling us that the early development of the universe was much more rapid and complex than depicted in textbooks. This is merely the tip of the iceberg among the many astonishing discoveries made by the Webb telescope. Confronted with these observational evidences that cannot be explained by the standard cosmological model, some scientists have started to question the universality and integrity of the Big Bang theory. Consequently, they have proposed that the universe might have undergone a periodic process of multiple destructions and rebirths, presenting a perspective that is radically different from the traditional linear cosmic history. Professor Roger Penrose, one of the leading figures in this theoretical revolution, put forward the conformal cyclic cosmology long before the observational results of the Webb telescope were announced. He contends that the universe continuously experiences a cycle from the Big Bang to the heat death and then to the next Big Bang. He also claims to have discovered concentric circle structures in the cosmic microwave background radiation, which he believes could be remnants from a previous universe, like an echo from a bygone cosmic era. When the Webb telescope directed its gaze towards the sky in the direction of the Big Dipper, it captured a series of faint and ancient light sources. These starlight rays, having traversed over 13 billion years of time and space, exhibit characteristics of being born too early, being too large in volume, and having too great a mass, far beyond the limits acceptable by current models. These celestial objects appeared in the first few 100 million years of the universe's history, during the so-called Reincarnation period. Their energy output, spectral characteristics, and structural properties indicate that they are extremely young galaxies, yet their level of maturity is truly puzzling. According to theory, early galaxies should have been in an embryonic stage, but the observational results show that they already possess a mass and structure comparable to that of the Milky Way. This phenomenon of temporal misplacement has left researchers bewildered. According to the Lambda-CDM standard cosmological model, when the universe was only a few 100 million years old, there had not been enough heavy elements and gas clouds gathered to form such large and stable galaxies. These observational results almost directly conflict with the existing theory. Thus, these galaxies have been jokingly referred to as universe breakers because their existence defies the boundaries of current physical laws, compelling the academic community to re-evaluate the formation conditions of the early universe. However, this is just the beginning. With the Webb telescope's in-depth exploration of the early universe regions, the super-aged galaxies discovered by astronomers are not isolated cases, but rather a whole batch. Their large number and significant mass can no longer be explained by chance or statistical errors. At the same time, the measurement of the universe's expansion speed shows a significant deviation from theoretical predictions, further revealing the fundamental blind spots in our understanding of the overall structure of the universe. The expansion speed of the universe is quantified by the Hubble constant. According to theoretical modeling calculations based on the cosmic microwave background and the early universe, the Hubble constant should stably remain within the range of approximately 67 kilometers per second per megaparsec. This is the result of precise deductions from the standard model and is also supported by high-precision data from observational missions such as the Planck satellite. However, when scientists use independent observational methods, such as observing the distance luminosity relationship of type Ia supernovae, the surface oscillations of red giants, the bending of light paths caused by gravitational lensing, and the period luminosity relationship of Cepheid variables, the calculated Hubble constant is significantly higher, reaching approximately 73 kilometers per second per megaparsec. This discrepancy has triggered the Hubble tension crisis. Now, with its unparalleled sensitivity and resolution, the Webb telescope has joined the battle of precise measurement and once again confirmed the huge gap between the two measurement methods, making it impossible to attribute the problem to measurement errors or instrument biases any longer. If the measurement results from two sets of methods based on completely different sources, technologies, and physical theoretical foundations conflict with each other, then the problem may lie in our basic assumptions. This reveals the severe challenges currently faced by the physics community. Is our fundamental understanding of spacetime, matter, and even the universe itself still far from complete? When theory fails to align with real-world observations, a new theoretical framework may be inevitable. One of the most disruptive hypotheses comes from the forefront of multiverse theory. Perhaps the universe we inhabit is not an isolated and closed system, but rather interacts with other universes in a certain scale and dimension, and may even be in the process of merging. This is no longer a science fiction concept, but a new direction for explaining the abnormal expansion of the universe. According to this speculation, the initial expansion stage of the universe, that is, the Big Bang, might not have been triggered solely by internal quantum fluctuations. Instead, the young universe might have entered a larger mother universe with different physical constants and structures, resulting in the observed extraordinary expansion phenomenon. To test this hypothesis, theoretical physicists have developed multiverse interaction models grounded in quantum field theory and higher dimensional space geometry. These models simulate the effects that occur when the boundaries or dimensions of different universes overlap, and how these effects manifest in the gravitational fields, dark energy densities, and spacetime curvatures observable to us. If our universe is absorbing energy and spatial structures from another universe, it would directly lead to a rapid expansion of its overall volume. The resulting geometric and energetic changes would be misinterpreted by our observational instruments as an acceleration in the universe's own expansion. Remarkably, the expansion velocity curves calculated from this cosmic intersection model align more closely with the higher values of the Hubble constant measurements. They can even explain the abnormal growth of some early-stage galaxies, providing unprecedented empirical support for this theory. The data revealed by the James Webb Space Telescope is like a boulder cast into the dawn of the cosmos, sending ripples through the academic community's collective thinking. It has not only reshaped our understanding of the early universe, but also holds the potential to open the door to new cosmological theories. An increasing number of astronomers and physicists are coming to realize that while existing theories have guided us to a century of remarkable achievements, our knowledge of the universe's deepest structures and origins is merely the tip of the iceberg. Countless hidden factors may be awaiting the next revolutionary discovery. The Webb telescope serves as a reminder that scientific progress does not stem from the mere confirmation of theories, but rather from their ability to withstand the impact of unexpected data. Each observed discrepancy represents an alternative path to the truth. To truly grasp the significance of this cognitive revolution, we must journey back to the golden age of the universe's birth. In the earliest stages after the universe's birth, there was a period known as the Dark Ages. At that time, a dense sea of neutral hydrogen acted like a cosmic fog, absorbing all high-energy photons and blocking the view between celestial bodies. As a result, the universe remained in almost complete darkness and silence for hundreds of millions of years. Based on the latest models and observations, the reionization period is estimated to have begun around 300 million years after the universe's birth. Young stars and primordial galaxies started to release sufficient energy, gradually breaking the bonds of neutral hydrogen and awakening the universe from its dark slumber. Computer simulations show that during this stage, the first ionization bubbles began to form tiny channels within the hydrogen clouds, allowing some high-energy radiation to freely traverse interstellar space for the first time. This provided a precious window for our current observations. However, the ionized regions were extremely limited in the beginning. They were like bubbles of light in a vast ocean of darkness, only surrounding the earliest, born, most massive, and most energetic primordial galaxies. creating local halos without yet connecting to form a transparent network across the entire universe. This was the standard narrative established over the past few decades. However, through its JADE observation program, the James Webb Space Telescope captured a new galaxy designated GSC 111, whose position can be traced back to just 330 million years after the universe's birth. This discovery was like a bombshell, indicating that a mature galaxy with a high degree of structure and radiant energy had already emerged during what we thought was the chaotic early days of the universe. Even more astonishingly, the energy emitted by this galaxy contains a large amount of extremely high-frequency ultraviolet radiation, precisely matching the Lyman alpha spectral lines released when excited hydrogen atoms excite. In the early universe at such a high redshift, the appearance of this signal was like an ancient lighthouse announcing the galaxy's vigorous activity. Yet, these observations also give rise to serious theoretical conflicts. According to current cosmological models, at that time, the universe should have been filled with neutral hydrogen, acting as a thick fog that blocked the propagation of all ultraviolet and Lyman alpha photons. In other words, light of this frequency simply should not have reached our telescopes from such an early epoch and distant location. The propagation of Lyman alpha photons requires the universe to enter the reionization period, when a large area of neutral hydrogen is converted into ionized hydrogen, allowing such light to penetrate the depths of the universe without being absorbed. Most models suggest that this stage should not have begun until at least 500 million years after the universe's birth. Joris Wittstocks, an astrophysicist from the University of Cambridge and the lead researcher of this study, admitted that the result was completely unexpected, hinting at the growing gap between theory and reality. Against the backdrop of what should have been the Dark Ages according to theory, this galaxy shines as brightly as a lighthouse, with a distinct and intense Lyman alpha radiation profile, as if it has prematurely entered the transparent phase of the universe. This inevitably makes us question whether we have underestimated the formation efficiency of early galaxies or overlooked some crucial mechanisms. Kevin Heinlein, a co-author of the research paper, further pointed out that, based on our current understanding, such a galaxy simply should not have existed at this time, and yet it does. This statement highlights the sharp contradiction between observational facts and theoretical predictions. Moreover, the spectral data of this galaxy shows that the high-energy ultraviolet light it emits can penetrate a distance of up to 650,000 light-years. This implies that a vast transparent bubble had already formed in its vicinity. According to current simulations, only when a large-scale ionization of hydrogen occurs, creating a transparent bubble with a diameter of more than 650,000 light-years, can these high-energy photons travel freely. This suggests that the reionization process either started much earlier in the universe's history or progressed much more rapidly and vigorously than we anticipated. Such contradictions have sparked bolder speculations. Could what we observe be remnants from a previous universe? Could this be observational evidence for Penrose's cyclic cosmology? While the multiverse hypothesis is fascinating, this discovery also offers a more down-to-earth explanation. Perhaps low-mass dwarf galaxies played a far more crucial role in the early universe's energy output than previously thought. Their sheer numbers and collective effects might have been the driving force behind the universe's transition to transparency. However, the mystery remains unsolved. Current data cannot determine the origin of these intense ultraviolet emissions. Researchers propose two main possibilities. One is a population of primordial stars with extremely long lifetimes, high temperatures, and intense brightness, known as population 3 stars in theory. The other is active supermassive black holes lurking at the galaxy's core. The high-energy radiation generated as these black holes accrete matter could have dominated the reionization of the entire region. How should we make sense of the growing chasm between these observations and existing theories? As reality repeatedly shatters our expectations, does it signal that our understanding of the universe's overall structure and origin is still in its infancy? With an increasing number of observations contradicting the standard cosmic model, from discrepancies in galaxy formation rates to conflicts in expansion velocities, we are compelled to question whether some of our most fundamental physical assumptions are flawed. Could it be that the Big Bang wasn't truly the beginning of everything? At the core of Professor Penrose's vision is the idea that the universe isn't a one-time event, but rather undergoes an endless cycle of creation and destruction. Each Big Bang is an echo of the previous universe's demise. His conformal cyclic cosmology posits that the Big Bang is merely a convergence and reboot, a big bounce, after the previous universe reaches extreme expansion and all matter is completely transformed into photons. According to this model, as the universe continues to expand, stars burn out, black holes evaporate, and all massive particles eventually dissipate. What remains is a timeless sea of light and dark energy, creating a platform universe devoid of scale and structure. As Penrose's philosophical tenet goes, the disappearance of scale marks the birth of a new scale. When the entire universe becomes an ocean of light and energy, free from any reference frame or physical separation, it sets the stage for the next Big Bang. In this scale, less and mass, less and state, the universe reconfigures its boundary conditions, giving rise to a new expansion and a fresh cosmic cycle, much like a phoenix rising from the ashes. While this might seem like an elegant mathematical narrative, Penrose emphasizes that his theory isn't contrived. He claims to have found traces of a previous universe in real observational data. He believes that remnants of past universes persist in the background of our cosmos, much like fossils from bygone eras preserved in a new civilization. The answer, Penrose contends, lies hidden within the cosmic microwave background radiation (CMB). This faint glow envelops the entire universe, originating from the first light waves that cooled down around 380,000 years after the Big Bang. It still permeates the cosmos at a temperature of 2.7 Kelvin. The CMB is like an ancient cosmic photograph, capturing the universe's appearance as it emerged from its fiery infancy, and serves as a crucial key to understanding the universe's origin and early evolution. When analyzing the full sky images of the microwave background captured by the Planck and WMAP satellites, Penrose and his team claim to have discovered non-random circular spots. These spots exhibit temperature fluctuations significantly higher than the surrounding background, and their regularity defies explanation by ordinary cosmic structures. Penrose named these spots Hawking points, symbolizing the remnants of black holes that completely evaporated in the previous universe. The Hawking radiation they emitted endured as faint signatures in the new cosmos. Theoretically, as a universe approaches its entropy limit, even the most colossal supermassive black holes cannot escape. They gradually evaporate through Hawking radiation, releasing their stored energy into space. After the universe reboots, these radiation remnants become the physical traces of Hawking points. These photons scatter and diffuse during the early stages of the new universe's formation, then cool as the universe expands, eventually becoming frozen within the CMB. Like ancient symbols etched into the annals of history, they await decipherment by future generations. Based on observational data, these Hawking points appear as circular hotspots in the CMB images, roughly the size of a full moon. Their irregular yet somewhat symmetrical patterns seem to whisper the universe's past memories. These patterns are precisely the observational findings that Penrose and his team have long pointed out. They believe these spots provide significant evidence for the cyclic nature of the universe. However, not all scientists are convinced. Despite the intriguing nature of the observations, the interpretation of these spots remains controversial. Some researchers argue that they could be statistical flukes or related to the initial quantum fluctuations of our own universe. In response to these doubts, Penrose remains calm and resolute. He notes that in the early 20th century, black holes were dismissed as absurd theoretical fancies, yet they later became indispensable entities in astronomy. Perhaps one day, Hawking points will also transition from theory to empirical verification, becoming a crucial piece in our understanding of the universe's cyclical nature. When we gaze up at the starry sky, it's as if we are looking at a silent epic. Yet, all we can decipher are just a few fragmented pages of this grand narrative. The James Webb Space Telescope has revealed not only ancient images from the dawn of the universe, but also a series of questions that have the power to shake the very foundations of cosmology. When we observe galaxies that shouldn't exist, structures that seem too old, and mysterious radiation in the starlight from 13 billion years ago, does it mean that the cosmic history we understand is merely a fragment of some larger cycle? Penrose's theory of Hawking points may be audacious, but it serves as a reminder that if every end is, in fact, a beginning, then our universe is but one link in an endless cycle of rebirths. Where did we come from? Which cycle are we currently in? Perhaps we are the forgotten memories of the universe, adrift in the tides of time, striving to rediscover our primordial light. After all, when you see the first glimmer from the depths of the cosmos, it might not be the dawn of a new era, but rather the rebirth of something far more ancient.